So we're continuing on with conic sections, and now we're going to look at ellipses. So we're going to be given the equation of an ellipse, and we're going to look at finding the equation that would give us information about where the center of the ellipse is, where points of vertices are, etc. So let me pull up in front of us an ellipse and the definition of an ellipse. I just noticed that I wasn't recording while I was explaining all of this, so I'm just gonna maybe quickly just go through it so that it's on the video. But we have an example of an ellipse. There are important points that are gonna help us graph this. So finding out where the center is, if it's in this form where it's elongated this way, we have x minus. Now everything is frozen. Now, let's see if it works now. So I have x, there we go, x minus h quantity squared all over a squared plus y minus k quantity squared all over b squared equals 1. Center is at this hk value. Locating which value is bigger in the denominator. So if a squared, if a is bigger than b, the bigger number is underneath the x. It's elongated with the x-axis. Our major axis has a length of 2a. So from the center, we would go over a units to the left and a units to the right. And so those vertices on the major axis, we're going to look at h plus or minus a comma k. Vertices on this minor axis, so going up and down a unit of b, the length of the minor axis is 2b. We're affecting the y value of our center. So from the center hk, we would go up b units and down b units. And so we would have h comma k plus or minus b. Foci, we would get c squared, or c, we take the square root, it's a length, is equal to the square root of a squared minus b squared. If our ellipse is elongated with a y-axis, our center is again at hk. Our equation is the same, but in this case, our b value is bigger than a. So knowing what the center is, hk, we can go up a units, or actually b units, to get our points on the vertices of the major axis. So going up and down b units is affecting the y value. So those vertices are going to be h comma k plus or minus b. The minor axis, we're going to go over a units to the left and to the right. That's affecting the x value of our center. So from there, our center hk, you're going to add or subtract a comma k to get these two vertices along the minor axis. So going back to the definition of an ellipse, I kind of wanted to show you a visual. And so back to the definition up here, just in case we didn't get to that. And I thought it was recording, but wasn't. Let me just read through this again. So an ellipse, basically, your set of all points in the plane whose the sum of the distance from two fixed points, A and B, are a constant. So these two fixed points that they're talking about are the foci. So if I take the distance to find any point on the ellipse, so right here, and I took this distance from one foci to that point on the ellipse, let's call it d sub 1, to this foci to the same point, let's call it d sub 2. This point, or this distance, from one foci to that point plus the distance from the other foci to that point is always going to be the same constant c. So let me show you a visual. I'm changing my screen here. So you should see in here the picture of an ellipse. So kind of imagine that on these foci, you have a tack or a pin, and you have this piece of string. And the string, what we make it taut, and we move that pencil around, we would be getting this image of the ellipse. And so in this case, you can see the sum of the two distance in this case is always going to be 8, no matter where I put it. And so by taking these two distance, always summing to 8, we would get the shape of an ellipse. So in front of us, we have an equation, 9x squared plus 4y squared minus 18x plus 16y minus 11 equals 0. We want to analyze this graph, find the center, foci, the vertices of each ellipse. In this case, just this one ellipse, and we want to graph it. So you should be aware of just looking at the equation, what shape that you're going to get. I know that this is an ellipse, and I'll go more in detail about this as we look at hyperbolas and put this all together. But I know this is an ellipse because I have an x squared and a y squared. If I just have an x squared or a y squared, I know it's a parabola. I know it's not a circle because the coefficients in front of my x squares and the y squared are different. If we have the exact same number in front of those, we have a circle. If they're different numbers but the same sign, it's an ellipse. So these are different numbers, but they're both positive in front of the x squared, y squared, so I know it is an ellipse. So the equation in front of us is 9x squared plus 4y squared minus 18x plus 16y plus 11 equals 0. We want to put this in the form that we can tell what the center is, and then we can locate where these vertices on the major and minor axis are, and then we can graph this. We need a perfect square for our x terms, and we need a perfect square for our y terms. And so let's group our x terms together, and let's group our y terms together, and let's get the constant on the other side. So rewriting this, we have 9x squared minus 18x plus 4y squared plus 16y, and adding 11 to both sides of our equation, this is equal to 11. In order to complete the square, recall the coefficient in front of the x squared or y squared in this fact has to be 1. So I need to factor out that 9, and I want to factor it out of all the x terms. So factoring in a 9 from this 9x squared minus 18x, we get 9 times the quantity x squared minus 2x. I'm going to add something in here to make this a perfect square. And leave some room there. Plus, so I want to factor the coefficient out from the y terms. That coefficient in front of the y squared is a 4, so I'm going to pull a 4 out of both of those y terms, so we get back the quantity y squared plus 4y. I'm going to add something in here to make it a perfect square, is equal to 11. So let's figure out what we're going to add to make these a perfect square. And recall, if we add something to one side of the equation, we have to add it to the other side of the equation to have equations remain equivalent. So now that I have my coefficient in front of my x squared 1, I'm looking at my middle term, which is negative 2x. I'm dividing negative 2 by 2. That's negative 1. So the same number I'm adding to get negative 2 is negative 1. Now we're going to square that number. So negative 1 times negative 1 is 1. But technically, on this side of the equation, I didn't add 1. I added this 9 times this one, because that 9 would technically be distributed. So over here, I'm taking that 9 times the number I added inside the parentheses. So same idea, I'm going over to my y terms, and now I'm looking at it. My middle term is 4. Divide that by 2 is 2. 2 plus 2 is 4. Now to add the number that would make this a perfect square, I'm going to take that number 2, square it, I get 4. Technically, though, I didn't add 4 on this side. I added 4 times this 4 out here. So that 4 would have to be distributed if I dropped those parentheses, and that would have given me a 16. So let's rewrite this one side. So this is 9 all times. Well, this is a perfect square right here. So the factor I can square is x minus 1, quantity squared, to get back x squared minus 2x plus 1, plus 4 all times. So this is also a perfect square. This is y plus 2, quantity squared, equals 11 plus 9 plus 16. Well, 11 plus 9 is 20, and 20 plus 16 is 36. So this is equal to 36. These ellipses are not in standard form until they're set equal to 1. And so this is equal to 36. So to make that equal to 1, I'm going to divide each side by 36. And I'm going to put the 36 underneath each grouping of those quantity squares. And so now let's reduce. So for that first fraction, 9 goes into 36 evenly 4 times. So I have x minus 1 quantity squared all over 4 plus, well, over here, this 4 goes into 36 9 times. So I'm left here with y plus 2 quantity squared all over 9 is equal to 1. So it's now in that standard form. You do want to make sure that you reduce this, because in standard form, that coefficient in the numerator in front of the square is 1. Okay, so now we have this reduced. We should be able to tell what the center is. The center is HK. And in our fact, H is always with the X values, opposite sign, so 1. K is always with the Y value, opposite sign, so -2. So locate the larger denominator, and that's going to tell us if the major axis is parallel with the x-axis or the y-axis. The larger number in the denominator is a 9. So 9 is bigger than 4. So I know that my shape of my ellipse is elongated this way. So in this case, I have b squared equals 9. So take the square root, I get b is equal to, normally I put plus or minus 3, but it's a distance, so I'm going up 3 and down 3 from my center. So to get the vertices on the major axis, going up and down from the center, I would still have the x value of 1, but -2 minus 3 gives me -5. And the other vertice, 1 is still the x value, but now I have -2 plus 3, which is 1. So my minor axis, combine my value here. So a squared is equal to 4, a is equal to 2. So I'm going to go left and right 2 from my center. So vertices on the minor axis, so we're adding and subtracting 2 from my center. My center again was 1, -2. So 1 minus 2 gives me -1. Y value stays the same, -2. So 1 plus 2 would give me 3. Y value stays the same, -2. So let's plot what we have. We have a center at 1, -2. Finding the points on our plotting our vertices. So we have a vertex at -1, -2. At 3, -2. Major axis, we have 1, -5. And we have 1, 1. So joining our points on our vertices, we get the following shape of our ellipse. So looking at the following example, we're given information about the ellipse and we want to find that equation. And so we're given that the center is -3, 1. We're given that the vertex, one vertex, is -3, 3. And we're given that the focus is -3, 0. So again, let's plot what we're given, and that way we can kind of tell which way is our ellipse going. Is it elongated the long way with our x-axis, or is it elongated the long way with a y-axis? And so plotting these points, I know my center is at -3, 1. So going to the left 3, up 1. I have this point here. I have my focus is at -3, 0. Okay, the focus is always on the major axis of an ellipse. So right there, I know that my elongated version is with the x-axis. So the larger value in the denominator is going to be with the x-axis, which will be in this case A. So far, let's put what we have. So my center, my h and my k value, I know h is -3, and my k value, because we're given the center, is 1. So I know I have x minus h. So x minus a -3 actually gives me a +3. And then plus the other perfect square is y minus k. So y minus 1. Again, I know that the larger value is in the denominator of the x's. We have an a squared and we have a b squared over here. A is bigger than b. We have a vertex at -3, 3. So go up 3. So since I'm going up and I'm not going left or right, I'm actually finding my b value here. My b value is that distance between my center and the vertex on the vertice of the minor axis. So I went up 3 here. So I know my b value is 3. Then I know b squared is equal to 9. So right now, underneath the y minus 1 quantity squared, I can put b squared, which is 9. The other information that we were given was about the focus. The focus is the value of c from that center. And so from -3 to 0, I get that c is equal to 3. Okay, C though is equal to the square root of the larger value, a squared, minus the smaller value in this case, which is 9. So I want to figure out what A is. Once I know what A is, I have this equation of my ellipse. And so I can put in here 3 is equal to the square root of A squared minus 9. So if I square both sides of my equation to get rid of that radical, I have 9 is equal to A squared minus 9. Let's add 9 to both sides. I get 18 equals A squared. Well, I could find out what A is, but I really just want to know what A squared is, because for the equation, we're going to be x plus 3 quantity squared is over A squared, which we just found to be 18. So with the information about the ellipse, we were able to find the equation of that ellipse.